to insertion operation. So right now, we need to study the insertion operation. All right, so let's look at the detail of the insertion operation. What do we really need to do for an insertion operation? Yeah. Based on our intuition, we can see we need to do these two things. First, find the right position. Okay. Where to insert, right? You need to find the position in the current array that we need to insert a new element. That's the first step. Second, move elements. You need to leave one element location, position, empty slot for the new element, right? You need to do that. How do you do that? You need to move some elements. So that's the second step. Move elements. Then put that new element in that slot. So that's the whole insertion procedure. Now let's look at the implementation details. So when we understand in these two steps, let's work step by step. All right, the first step, how to find the correct position for the new element. So let's look at this diagram. The array already sorted. We want to find location in the current array. Where should we insert this new element? When we do that, think about there are two ways to do it. There are two ways to do it. So here, let me give that two basic ways to do it. The first way, you compare one after another. You look at the first one, the second one, if greater or smaller, right? Next one, greater or smaller, okay? So that way, we recall our linear search because we do the search. Find correct position. Is that a search operation? What you do is just a search, right? Search for the correct location. When you do search, there is a linear search way, right? Yeah. So the first way, that's the linear search way. Linear search way. Okay? Yeah. All right. Then the second way. Can we jump faster? Can we do not start from the first one? Can we start from somewhere in the middle and do the search? So the binary search. Because the array already sorted. If array is sorted, we can apply binary search. I think you know the binary search. But for this module, at some later part, we will study the binary search completely. Yeah. Also divide and conquer. Yeah, it's a good divide and conquer example. Yeah. But at this point, we need that binary search idea here. Okay? Yeah. So the second way is the binary search way. Okay, yeah. Two ways. Yeah. These two ways, you can see, definitely, this is faster, right? Yeah. Definitely, binary search is faster than linear search. No question of it. Yeah. So it looks like we should pick the binary search But just a minute. Do not make that decision that fast. Why? Because that is just the first step. Then you need to move. After the first step, you need to move elements, right? When you move elements, you have to move element one by one. That is the linear way, right? When you move elements, you still use the linear way. Yeah. So that means even you can save some time in the first step, you will give it back at the second step. So that means here, the binary search way may not help you much because you have a very slow second step. Okay, yeah. So for that reason, it's a pity we cannot use binary search way here. Yeah, we cannot. Yeah, because the element move step very slow. It's a linear way. This is a linear way. Okay, since this is a linear way, so we can combine this step with the first step together to do it at the same time. So that means the binary search way won't help much. So we cannot get any benefit from the binary search way. But, although we cannot use it, but that idea is really good. So that binary search idea, so let me call it. So binary search insertion, binary search based insertion. Okay, yeah. So we better call binary search based insertion. So this idea is very useful, interesting. So we need to save it somewhere in your memory, in your brain, because later we have chance to use it. So it's a good idea. Okay, yeah. All right, so let's move to the second step. How to move the elements to make the new array sorted. Yeah, that's pretty straightforward. Yeah. All right. So in our next slide, I will use a diagram to show you how to move. Yeah. But before we go there, I want to do some analysis a little bit, because this step, move, search, combined, this step, the average cost is big theta of k. Big theta of k. Yeah. Yeah. Why is that? Yeah. We will see. So what is the average case efficiency? This question. Yeah. Is it k over 2? Yeah. Because usually, based on our basic understanding, yeah, for things like this, yeah. The best case 1, the worst case k comparison, right? So the average pretty much k over 2, right? Yeah. If you just want to approximate the answer, it is okay. K over 2, that's the good approximation. But if I ask you precise answer, what is the average case efficiency precisely? Precisely, the expression, precise expression. How to get that? Yeah. Here, I want to show you how to get it. Okay, how to get it? Yeah. All right. So let me draw a line. Insertion. So we already have k elements, A0, A1, A2, k minus 1. When we talk about insertion, how many possibilities for the location of ak? How many possible different locations we can put ak? Yeah. So you will see there are k plus 1 slots we can consider. 1 slot, 2 slot, between every 2 of the adjacent elements, we have 1, right? We have 1, okay? We have 1. Then the last one, okay? And we assume for each slot, the probability the same. Equal chance to be in any interval, okay? Yeah. To get into the first interval, we need 1 comparison, right? Getting to the second interval, we need 2 comparisons, and so on, 3 comparisons, and so on, okay? All right. Then, this slot, we get k comparisons. And the last one, we also get a k comparisons, not k plus 1, because we don't need to do another comparison. We only have k elements, right? So you don't need to compare k plus 1 time. The maximum number of comparisons, k, right? So we have k, k, repeat twice. Now we take the average of these k different cases. The average is 1 plus 2 plus all the way through k plus another k, divided by k plus 1. Okay, yeah. Then we apply the summation formula for the first k numbers. 1/2 k times k plus 1 plus k divided by k plus 1. Okay, how about that? Then this one we can write, yeah, because we can separate, right? The first part we get 1/2 k. The second part, k over k plus 1, right? K over k plus 1. Is this number close to 1? Yeah, because only one short on the denominator. So this number approximately 1/2 k plus 1. So the average, a little better approximation than that one, 1/2 k plus 1. But no matter plus or not, it's all big theta of k. Okay? Yeah. So that's the way we find the average. Okay? All right. Now let's move to the next part. We want to look at the shift elements for insertion. You need to make some room for new element. Yeah. Shift to the right. Yeah. Shift to the right 1 by 1. Yeah. So let's look at what kind of operations do we need to complete this step. Yeah. All right. When we start, we have this situation. Yeah. In order to do the insertion, we need to do shift, so we need to do some preparation. To do the preparation, yeah, so let's consider, so this location, yeah, suppose the new element should be here, right? Let's imagine the new element should be here, okay? Yeah, we just assume, okay? Yeah. Then, the first thing, we need to lift AK element to a new variable. Yeah, so here we create a new variable here. So we copy. So this is one copy operation. Copy to the new variable. Okay. After the copy, this room is empty, so we can make the shift. Shift AK minus 1 to its right adjacent location. So we need one assignment, another assignment. Then another shift, another assignment, and so on. After the last shift operation, another assignment. Now we leave some empty location for the new element. All right, that's the AK. Then we need to make the last assignment to this place. And we finish the insertion. The number of assignments for this situation, we consider the average case big theta of K. That's the analysis we did in the previous slide. After this, we complete the whole insertion operation. But you can see, if we repeat this insertion many times, from smallest problem size to the whole array, it's already there. That's the insertion sort. If we do this insertion operation many times, up to, so let's look, how many times do we need to do? n-1 times, right? Is it n-1 times? Because the first element, you don't need to do it, right? The first, starting from the second element, for every element, you need to do one insertion. Every time you need to do one insertion. Total, you'll do n-1 insertions. After this many insertions, you get a whole array sorted. Okay, so that's our 8.2 insertion operation. So we have our last video, 8.3, to complete the insertion sort. Some final discussion. All right, so to finish here.